Let us now discuss exponential functions. Take note that a to the n is equal to a times a times a times ellipsis times a, where a is the base, n is the exponent, and these ones here are n factors of a, and a is element of real number and n is integers. It means that a to the 0 is 1, since any real number raised to 0 is equal to 1 except for 0, because 0 to the 0 is indeterminate. Then we have a to the 1 is a squared is a times a, and so on. Now if we have a function f of x equals a to the n, where a is real number and n is integer, what kind of function is this? An exponential function? Are you sure? Let's look at this in this way. What if f of x is a to the 0? What kind of function is this? Take note, a to the 0 is 1. And f of x equals 1 is, yes, a constant function. How about f of x is equal to a to the 1, which is a? Again, a is any real number. So therefore, this is just, yes, a constant function again. How about f of x equals a squared? Quadratic. Take note, guys, that a squared is just a times a, and real number times real number is also a real number. So therefore, this function here is also a constant function, and so on. So therefore, our f of x equals a to the n is just a constant function. Now, what will happen if our base is a variable x? What if our f of x is equal to x to the 0? Again, x to the 0 is 1, and this function here is a constant function. And what is f of x equals x to the 1, which is x? Take note, guys, this is just f of x is equal to mx plus b, where m is 1 and b is 0. And this function, and function in this form, is called, that's right, linear function. And what is f of x equals x squared? What kind of function is this? Yes, this is quadratic function. And f of x equals x cubed is just cubic function, and so on. Quartic function, quintic functions, and x to the n, which is actually a polynomial function, the general form of polynomial functions, where a's are 0 except for a to the a sub n. And again, the graph of this constant function is just a horizontal line. This f of x equals x is a straight line with inclination, since m is greater than 0. Then this one is a parabola that opens upward, and this one is like this, the graph of Q, so on. Next, what if the variable is our exponent? Example, f of x is equal to b to the x. Say f of x is equal to 2 to the x, f of x is equal to 2 to the negative x, f of x is equal to 3 to the x, f of x is equal to 10 to the x, f of x is equal to 100 to the negative x. What kind of functions are these? Okay, that's correct. These functions are what we call the exponential functions. Now let us define exponential functions formally. So the equation f of x equals b to the x, where b is greater than 0 and b is not equal to 1, defines an exponential function for each different constant b called the base. Then the independent variable x may assume any real value. So the condition, the restrictions b greater than 0 here and b is not equal to 1 are very important, because if b is equal to 1, what will happen to our f of x? Example, f of x is 1 to the x. Take note, if x is 1, that is just 1 to the 1, that's 1. If x is negative 1, that is just 1 over 1, which is 1. So basically that is 1, and that is just a constant function. And the b greater than 0 here is very important, because if b is negative, there is a way how to solve it or how to graph it, but we will be needing higher concepts in mathematics. So right now in this course, we will just be considering this exponential function as b to the x, where b is greater than 0 and b is not equal to 1. Now let's observe the behavior of the graphs of exponential functions. Suppose we have f of x equals 2 to the x and f of x is equal to 2 to the negative x. Okay, let's draw a rectangular coordinate system. Okay, this is our x and this is our y. Let's use tabular form or tabular method in locating the ordered pairs of the graphs of these functions. So first we have x, and this is our f of x equals 2 to the x. Now if x is 0, what is 2 to the 0? That is just 1. So we have 0, 1. This ordered pair here is 0, 1. Now if x is 1, what is f of x? That's 2 to the 1, that's 2. So this is 1, this is 2. This point here is 1, 2. Now if x is 2, what is our f of x? That's 2 squared, and that is 4. This is 2, 3, 4. This point here. This point here is 2, 4. Now what will happen if x is negative 1? So that is just 2 to the negative 1, that is 1/2. So here. And if x is negative 2, that's 2 to the negative 2, that is 1/4. So here. Now connect the points. these 5 points here are enough to draw the graph of this function. So this graph here is our f of x, which is 2 to the power of x. Now how about f of x equals 2 to the negative x? Let's use another color. Let's use blue. So this is our x, and this is our f of x equals 2 to the negative x. Now, if x is 0, what is 2 to the negative 0? That is just 1. So this point also. Now, if x is 1, that is 2 to the negative 1. That is 1/2 here. And if x is 2, that is 2 to the negative 2. That is 1/4 here. Okay. Next, what if x is 1? That is, or negative 1. That is 2 to the negative 1. That's 2 to the 1. That is 2. This one here. And if x is negative 2, that is 2 to the negative 2. That's 2 squared, and that is 4. So here. Now connect the points. And this graph here is f of x is equal to 2 to the negative x. Let's add another one. Let's use another color. Say green. X, and our f of x is 3 to the x. Okay. If x is 0, our 3 to the 0 is just 1. So this point again. Now if x is 1, that's 3 to the 1, that's 3. So 1, 2, 3 here. And if x is 2, that is 3 squared, that is 9. So we have, assuming like this, and this is 2, this is our, say, 9. Now if x is negative 1, that's 3 to the negative 1, that's 1/3. So here. And if x is negative 2, that's 3 to the negative 2, that's 1/9 here. Now let's connect the points. This, and this point here is f of x equals 3 to the x. One last. Let's have x, then our f of x is equal to 3 to the negative x. If x is 0, that's 3 to the negative 0, that's 1. So this point again. If x is 1, that's 3 to the negative 1, that's 1/3 here. Now if x is 2, that's 3 to the negative 2, that's 1/9. Next, if x is negative 1, that's 3 to the negative 1, that's 1, and that is 3 here. And then, if x is negative 2, that's 3 squared, and that is 9 here. Then connect the points. So this is our f of x equals 3 to the negative x. These graphs are almost the same with example f of x equals 10 to the x and f of x equals 10 to the negative x. So basically, the form of the graph is just like this for x positive and like this for x negative. Now, what can we observe about these graphs or about the behavior of the graphs of exponential functions? Before we proceed to observation or properties of exponential functions, let's find first the domain of these graphs. So what is the domain of this graph? Now, for any value of x, is the graph defined for any real number value of x? Yes, because every time you substitute a real number on x, there will always be a value of 2 to the x, which is also a real number, or b to the x. So in that case, we have the domain is all real numbers. How about the range? Yes, the range is from 0 to positive infinity, since the graphs here do not touch the x-axis. Okay, so the range is from 0 to positive infinity, but 0 is not included. So what can we observe about the graph of these functions? Let's call it properties, basic properties. Okay, that's right. All graphs pass through the point 0, 1. So all graphs pass through the point 0, 1 here. Okay. Next. Okay, all graphs are continuous. All graphs are continuous with no holes or jumps. So if you have watched the video that we just uploaded on rational functions, you would understand this function with a hole or holes or jumps. Next observation. Okay, now since the graphs do not touch the x-axis, what can you say about the x-axis? Okay, the x-axis is an asymptote. Particularly, it's a horizontal asymptote. Next, what can you observe for b greater than 1? What are b greater than 1? This one. 2 to the x and 3 to the x. 2 is greater than 1 and 3 is greater than 1. What can you observe about their graph? Okay, it's increasing. Okay, if b is greater than 1, then b to the x increases as x increases. Okay, next, how about if b is less than 0 and is greater than 0 and less than 1? Example, this one. So do not be confused with the negative exponents here. It only means that 2 to the negative x is just 1/2 to the x. And this 3 to the negative x is just 1/3 to the x. If you don't want to look at it in a negative way. So you can transform this one into 1/2 to the x and 1/3 to the x. So basically, these values here, this base here, are in between 0 and 1. So what can you observe about their graphs? Okay, that's right. The b to the x decreases as x increases. Now, what if in this graph we'll draw a horizontal line? Let's say this one. Okay. Let's draw a horizontal line. Just focus on one color there, or one graph of the equation. Example, the white one. If I draw a line here, how many points or point in the graph that it intersects? Exactly one. How about another line? How many points or point? One. Then, so regardless of how many lines you draw or how many horizontal lines you draw, they will only intersect at exactly one point in the graph, okay, of the graph of that equation. So therefore, based from our previous video or discussion, the f here, f is a one-to-one function. Okay. And what can you say about a one-to-one function? Okay. What can you imply, or what is the implication if a function is one-to-one? Okay. Now, if a function is one-to-one, its inverse exists. Okay. Its inverse exists. Actually, the inverse functions of exponential functions are the logarithmic functions, which will be discussed later on after this one. So remember these basic properties of exponential functions. For a and b positive, where a is not equal to 1 and b is not equal to 1, and x and y are real, so these are the exponent laws. A to the x times a to the y is equal to a to the x plus y. Then a to the x quantity to the y is equal to a to the x times y. Then quantity ab to the x is equal to a to the x times b to the x. Then the quantity a over b to the x is equal to a to the x over b to the x. And then a to the x over a to the y is just equivalent to a to the x minus y. Okay, just to give a simple illustration, if a is equal to 2, x is equal to 2, and y is equal to 3, for the first one, this a to the x times a to the y is just 2 to the 2 or 2 squared times a to the y, that's 2 cubed. 2 squared is 4 times 8 is 32. Now, the a to the x plus y is just 2 to the 2 plus 3, which is 2 to the 5. And 2 to the 5 is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So they are equal. So this a to the x times a to the y is just equal to a to the x plus y. So you can create the same illustration by just assuming certain values of a, of x, and y. Also, a to the x is equal to a to the y if and only if x is equal to y. So it only means if a to the x is equal to a to the y, then x is equal to y. Also, if x is equal to y, then a to the x is equal to a to the y. So this is what we mean by if and only if. That's an equivalent statement. Third, we have for x not equal to 0, then a to the x equals b to the x if and only if a equals b. Now take note of these properties, the exponent laws, and these two additional properties, because these are very important in solving exponential equations. Example. Solve 4 to the x minus 3 equals 8 for x. So solution. Take note that we have this rule here. So we'll find ways that the exponents are the same but different base, or the same base but different exponent, so that we can have their corresponding equivalents. So in this case, it is hard to find an exponent of this expression here where the exponent is x minus 3, then the equivalent is 8. But we can find ways in creating the same base for 4 and 8 but different exponents. So therefore, we can write this one as 4 to the x minus 3 equals 8 implies 2 squared to the x minus 3 equals 2 cubed. Or this is, from this law, from this one, a to the x to the y is just equivalent to 2 times quantity x minus 3 equals 2 cubed. Now we have the same base here, so therefore we can apply the second property here. Since we have the same base now, the 2, we can apply the second rule, which is 2 times x minus 3 equals 3. Then simplify. 2x minus 6 equals 3. 2x equals 3 plus 6 divided by 2, x is equal to 9 over 2. Or your solution set is 9 over 2. Another example. Solve for x if 2x plus 1 cube equals 8. So in this case, our variable is on the base of the exponential expression, and our 8 here has no variable. So we will find ways that we can express this 8 where the exponent is 3, so that it is the same with the exponent of 2x plus 1, so that we could apply the third property. So here we have solution. 2x plus 1 cube equals 8 can be expressed as 2x plus 1 cube equals 8 can be expressed as 2 cube. So they have now the same exponent, so therefore we can use the third property, which is 2x plus 1 equals 2. We have 2x is equal to 2 minus 1. 2x equals 1 divided by 2. X is equal to 1/2. And our solution set is 1. Let's have these practice problems. you can solve these ones on your own. Now there is this exponential function, a special case of exponential function, which is the exponential function with base e. So let's define this one. So for x, a real number, the equation f of x equals e to the x defines the exponential function with base e. So if the graph of this, if we have, say, this is our rectangular coordinate system, this is x and this is y. This y is equal to e to the x. Still we have y is equal to e to the x. It still passes to 0, 1, because when x is 0, e to the 0 is just equal to 1. So still almost the same with the other logarithmic functions. This is y is equal to e to the x, and this one here is y is equal to e to the negative x. So you can just substitute, you can just make tables again, like the one what we did a while ago. F of x is equal to e to the x. What are the values if that's negative 2, negative 1, 0, 1, 2? Okay, what are the values of our e to the x? And basically, the form of the graph is still in this one. So we have practice problem again. Try to graph this one on your own. F of x is equal to 4 minus e to the x over 2. Just use this tabular form. When x is 0, when x is 1, and so on. Just use random values so that you would be able to find the ordered pairs in your Cartesian product or Cartesian plane, where if you connect them, that's the graph of that particular function. Note that what we have mentioned a while ago on the characteristics of functions, f is a one-to-one function, and therefore its inverse exists. And we have mentioned a while ago that the inverses of exponential functions, or the inverse functions of exponential functions, are actually the logarithmic functions. Now suppose we have f of x is equal to 2 to the x. Now if we let y is equal to f of x, this one here is y is equal to 2 to the x. Now if we try to interchange, if we interchange x and y, what will happen here? This y is equal to 2 to the x becomes x is equal to 2 to the y. And this x equals 2 to the y is actually the inverse function of f of x equals 2 to the x. And this one here is again a logarithmic function. Logarithmic function with base 2 here, with base 2. And therefore that can be written as y is equal to log to the base 2 of x. This is read as log to the base 2 of log is the notation for logarithm. Now if we take the values of x for f is equal to 2 to the x, that like what we have done a while ago, for x negative 2, our f of x is 1/4. For x negative 1, that's 1/2. For x 0, that's 1. For x 1, that's 2. And for x 2, that's 4. And the graph of that, if we could just repeat the graph of that. So we have x and y. So again, for 0, 1, this is 0, 1. And negative 1, 1/2. Negative 1, 1/2. And then negative 2, 1/4. And then 1, 2. And then 2, 4. Connect the points again. And this is our f of x equals to the x. Now since the inverse, okay, take note, this is the domain, from the domain, and this is from the range. Take note that for the inverses, or for the inverse functions, the domain of the original function is the range of its inverse, and then the range of the original function is the domain of its inverse function. So if we have x here, and this is our so if we have x here, which is 2 to the y, and this is our y, if x is 1/4, our y is negative 2. If x is 1/2, our y is negative 1. If x is 1, our y is 0. If x is 2, our y is 1. And if x is 4, our y is 2. Okay? Take note of this. The range of the original function is the domain of the inverse, and the domain of the inverse function is the range of the original function. Okay, now, if you try to locate this one, when x is 1/4, let's use another color. Choose blue. When x is 1/4, y is negative 2. If this is 1/2 and this is 1/4, y is negative 2. 1, 2 here. Now if x is 1/2, y is negative 1 here. Now if x is 1, y is 0. Then if x is 2, y is 1. If x is 2, y is 1. And if x is 4, 3, 4, y is 2 here. So if we connect that one, this is the form of the graph of the inverse of f of x equals 2 to the x, or the logarithmic function, which is this one. So this function here is inverse function. So as you can see, this graph here is symmetric through this line. Again, take note guys, is symmetric through this line. Take note, the original function and its inverse is symmetric through the line y equals x, based from our previous. So again, the domain of this is all real numbers, and the range is from 0 to positive infinity. So therefore, this is for the function. So therefore, for the inverse of that, which is this one, the blue one, is from 0 to positive infinity, and its range is all real numbers. Okay, all real numbers. It will go down from this point to here, and the range is all real numbers. And then the domain is just from here to here. So that's why that's from 0 to positive infinity.